It's nice to see you. It's also National Burrito Day. Wanted to wish you all happy National Burrito Day. We have a decent amount of stuff to do today, just to let you know kind of where we're at. We are going to finish the discovery of the universal law of gravitation today. So we're going to get that all figured out, be as smart as Newtons, because that's what we do. We're going to do a couple of problems, and then, friends, please stop talking. Please stop talking. And then we may also get into electrostatics today as well. The reason that I was going to do that, I was trying really, really hard to get through the free response questions to get them back to you today from the final, but I was doing a bad job of grading, and I think we can all agree that me doing a bad job of grading is probably not what you would want. So I'm going to get them done tonight. I will get them back to you tomorrow. So this is what is on the calendar for tomorrow, but I wanted to make sure that we had time to do it all, so we may or may not get to that tomorrow as well. What's up?
What about the multiple choice?
I will get it all back to you at once. But the multiple choice is easy graded, right? So I don't have to work hard at that. But I wanted to get the whole thing to you. Yes. So tomorrow, I promise, will happen. It just was not. It was not in the cards for today. One of your classmates asked if there was homework or if there is homework. Yes, there has been homework for the last few days, and I just haven't put it up here. I apologize. Sometimes I get in the habit of that, and sometimes I get rushed, and that's my situation right now. So it's all up on Canvas. There will be a couple more assignments based on the electrostatic stuff that has not been put up yet, but I will put up. But just so that you are aware kind of where we're at schedule-wise in this class and kind of where we're at right now, we are still in this circular motion business. It's been kind of a secret circular motion thing because we did it for a while, and then you did your final. And then we started talking about some other stuff. But this is all really related to circular motion, which is why we're doing it all together. So just a friendly reminder that we did all this circular motion business, this inertial and gravitational mass, weightlessness. We're going to do gravitation. We're going to do Coulomb's law. We've got a lab and a little bit of stuff. This is really not very much. We will be testing for sure middle of next week. Okay? I'm going to guess Wednesday, Thursday. I don't know if we're going to need an extra day for this because that's pretty straightforward. We'll see. So it'll kind of depend on how far we get today and that sort of thing. Okay. But we'll for sure be testing by the end of next week, middle of next week. And then we've got one more super short unit, and then we're going to start reviewing. And then it's going to be happening because by the time I see you on Tuesday or Monday, it's like a month until the AP exam. Woo! It's going to be great. So we got to get going. Is that making sense? So again, I'll put a couple more assignments in here. I just have not done that yet because I haven't sat down to do it. So many things to do in life. Oh, dear. Okay, so at this point right now, you need your notes out that we started yesterday that have that big, nice triangle on them. You will absolutely need a calculator today, so make sure that you have that in front of you, okay? Get that stuff out so that you can get started. You can get ready to go. So a friendly reminder of where we've been, because I haven't stared at this for about 23 hours, and probably that's the case for you as well. Remember that we were telling the story of Sir Isaac Newton prior to him being a sir. He was sitting under an apple tree. The apple fell and hit him on the head, and he said, "I've discovered gravity." Not really. The apple fell and hit him on the head, and he looked up and he saw the moon, and he said, I wonder if the moon is falling too. Hi. You just said it right there, and I'll get it in a second. Thanks so much. So then I asked, as he did, for you to figure out for me, how far will the moon fall in a day? It was so astutely stated that a day was 24 hours, and we could convert that into seconds, and we can find that the moon was going to fall 3.7 times 10 to the 10th meters. That is assuming that it's falling at an acceleration of 9.8 meters per second squared. Okay? Prior to that, we didn't really have any good evidence that 9.8 meters per second squared was wrong. Okay? Remember that we did this. We measured that 9.8 by dropping stuff off of railings. And they'd been doing that for years and years and years before Newton, right? So they got a pretty decent value, but they didn't really have any good reason to think that it was going to be different anywhere else. The subtle differences that G has between, sea level and the top of a mountain are so subtle that with the equipment that they had at the time, they weren't really, the statistical noise was too great to be able to say, oh, yeah, G is really, really changing from one place to another on Earth. So sure, why wasn't it just always the same? Well, because that means that the Earth falls through the moon falls through the Earth on its orbit, which does not happen. Okay? Question? Are you good? Okay, I just want to make sure I wasn't missing. Okay. So then the next question that I asked you, and this is where we got to yesterday, was how far does the moon fall in 24 hours? If it doesn't fall at an acceleration of 9.8 meters per second squared, how far does it fall? And from that, the question that I'm going to ask you with that is, what's the acceleration then? So I think that we got to this point before we left yesterday, but is everybody okay with a value of about 1 times 10 to the 7th meters for the distance that the moon actually falls? Does anybody need me to go through that, or are we okay?
Like that.
You would like me to go through it quick? Okay, so yeah, I'm gonna go kind of fast, but I will absolutely do it. So we know that the distance between the moon and the Earth doesn't change very much because it's going in a circle. So this distance DME, okay, which we had up here, is about constant. But if for some reason we snapped our fingers and there was no gravitational force, this moon that was going around in a circle, it would be like if I cut the string, right? The moon is just going to go in a straight line. And I can find out how far it goes in a straight line because I know how fast it goes. Okay? So I can find the speed of the moon using this right here. I know that the moon goes all the way around in its orbit in 28 days. Okay? And that's 2 pi r. That's the circumference of the circle. So 2 pi r meters in 28 days. So I can figure out how fast it's going. And from that, then I can figure out how far it goes in 1 day. Or what fraction of that it would be going in 1 day. Okay. Using that, now I've got 2 sides of a right triangle. Courtney, you just made a funny face. Can you tell me what's going on?
So I get my velocity and divide it by 28. Is that what I'm supposed to do?
So you got your velocity is going to be in like meters per second then, right?
Yeah.
And then you're going to multiply that by 24 hours. Or the amount of time for 24 hours to find the distance. Because that red line here, this one right here, that's the distance that the moon travels in a straight line without gravity. Does that make a little more sense to you? And you can say, not quite yet. Keep talking. I'm happy to do that.
Well, it's hard because I don't remember like where all these came from, so I don't know.
Sure.
Okay.
So? Okay. So this is the distance, and we can find that from using this, right? The speed and the time to find distance. So we can find that distance, and I can't remember what I got now. Let me look here. Got lots of things here. Something like 8.6 times 10 to the 7th, maybe. So that's this side here, the little short side of my right triangle. Not drawn to scale, just making that very clear, right? So we got the distance from the moon to the Earth. That's one side of my triangle. I've got the distance it would travel if it just went in a straight line. That's the second side of my triangle. And it's a right triangle, so now I can just use the Pythagorean Theorem to find my long side, my hypotenuse. So I got for my hypotenuse, I got 4.1 times 10 to the 8th meters. Which is kind of convenient since the distance from the moon to the Earth is 4 times 10 to the 8th. So it's just 0.1 times 10 to the 8th or 1 times 10 to the 7th. So that's this little distance. That's how far it fell. Is that better?
Sure.
Okay. So now, I know how far the moon has fallen. So I know my dy, right? That's this thing here. My initial velocity in the y direction of its falling is 0. My time is 24 hours. I want to know the acceleration. So this is 1.0 times 10 to the 7th. Can you solve for the acceleration? I'll give you a hint. It won't be 9.8. Do you think it's going to be bigger or smaller than 9.8? Smaller, probably. So go ahead right now using your brain and using your partners if you need a little guidance. You're going to use the nice big long equation that we know and love. This one right here. D equals VIT plus 1 FAT squared. But now you're going to solve for A. We are now finding the acceleration due to gravity at the distance of the moon from the Earth. Okay, I'm going to give you just a minute to work on that because I want you to get it. I don't want you to just rely on me. All right, my friends. So we did not get 9.8? No. Something a little smaller? Slightly, maybe a few orders of magnitude smaller. What did you get? Silence. I know you got something. 2 point something times 10 to the something something? No? 2.7 times 10 to the what? Is that what you got? Ish? So you got it like 0.0027. Did I have enough zeros there? Yeah. Meters per second squared. So either way you write this, and I kind of like writing it this way. So at the surface of the Earth, let's just kind of imagine this here. So here's the Earth, and if I have my little apple, again, not drawn to scale, but if I have my apple here, and it's falling, it's experiencing an acceleration due to gravity, right? In this direction, like towards the center of the Earth. And the acceleration due to gravity is 9.8 meters per second squared, right? Down. What does down mean? It just means towards the center of the Earth, center to center, right? It's not really center, but you get the idea. I put the moon way up here, though. Let's make the moon orange today. It's a little further away. Again, not drawn to scale, but you get the idea. The acceleration due to gravity up here is a little smaller because the acceleration due to gravity that it's experiencing here is 0.002, what do we say, 7? Meters per second squared. So with 2 data points, we can with certainty say that the acceleration due to gravity is not constant. Is that fair? Okay. With 2 data points, you know that if you were going to do a lab and you just got 2 data points, I'd be like, that's not enough data points. Now, in this case, it's kind of hard because we don't have other things that we know of. We don't have another satellite, natural satellite that's orbiting the Earth that we know about, right? That we can like measure and da-da-da. So maybe 2 data points is all we really got. My third question for you, remember, I don't know if you remember on Wednesday I told you that I had 3 questions. I had question 1 was how far does the moon fall in one day? Question 2 is how far does the moon fall in one day? Question 3 is not how far does the moon fall in one day. It is related though. Question 3 is how does the acceleration due to gravity vary with the distance? And part of the reason that I love this little conversation is that this is physics. Like, this is us trying to figure it out. You may have heard the rule. You may have an anticipation of what it is, but I want you to look at this with a blind eye in that way. I want you to think about this from raw data perspective, okay? We know that it varies, so let's start with a simple variance. We're talking about gravity and we're talking about distance. So very simple. We know it varies. So let's say that the acceleration due to gravity, do you guys know what this thing is? It's not alpha. It's proportional to, have I introduced this to you before? Yeah. I can't remember. Okay. Like way, way back when. G is proportional to D. Put a big question mark up there because some of you are laughing at me in your heads already, I can tell. Is the acceleration due to gravity proportional to the distance?
Yes.
Is it?
Yes.
If it is, I want to translate this for you. If it is, that means proportional to means there's a proportionality constant. So that means that we could say G is equal to some constant K times D. And that constant K should be the same for any data that we have. Okay? So I want you to think about that real quick here. Let's just kind of get our brains around what this is saying here. We are saying, we're going to draw a little chart because we're going to do some math here. We've got the acceleration due to gravity is 9.8 meters per second squared at a distance of, what distance are we talking about? The distance, what'd you say? To the center of the earth, because we're talking center to center. So I'm talking about the frog. He's sitting right here. He's very, very near the Earth's surface, right? All things considered, when you think about how big the Earth is, really we're darn close. So the acceleration, or excuse me, the distance to the center of the Earth, the radius of the Earth is about 6.38 times 10 to the 6th meters. Would you agree that whether I'm holding him 1 meter or 2 meters above the Earth, it's not going to matter, right? That's a lot of zeros out here where there's a 1 or a 2. It does not matter. So there's G and there's G. That's our data point 1. Data point number 2 was the other one that we had. That was, where did it go? It was 0.0027. I'm going to be a little more practical maybe and write 2.7 times 10 to the negative 3rd meters per second squared. And that one was, we said it was what, 4 times 10 to the 8th meters away. So this is kind of our data table that we're using. What do you guys think? Do you think that this is going to be true? That G times some constant will equal D in both cases here, the same constant? Ooh, never done this before, Miss K. Let's test it, okay? We're going to split the class. I'm going to feel like right here is going to be a good place to split, okay? So this side, you guys are going to be the apple people. You guys are going to be the moon people, okay? So apple people, I want you to find the constant K for the apple. So that's going to be this one here, the top one. Moon people, you're going to find the constant K for the moon. So apple people. And moon people.
Oh my god,
What happened?
I just realized something. We're good.
Are you okay?
I thought that was like a fraction this whole time. I was like, why are we just doing it? We're good.
Okay, I'm just making a chart.
No, yeah.
Okay, so apple people, you're going to do the acceleration due to gravity divided by D, right? Does that make sense? G divided by D, you're going to find out a number. Moon people are going to do the same thing, just the different numbers.
We're apple. Yeah.
Moon people talk to each other, make sure that you've got the same answer. Apple people talk to each other, make sure you got the same answer. Check, check, check.
I think it's 1+5 1,755.
You see, I know why you're wrong.
This constant, for our purposes, does not mean anything right now. But it is just saying that if this is true, that constant should be the same. The proportionality should be the same regardless of where we're at. So apple people, what did you get for K? To the what? Negative 6. And bless you. Moon people, what did you get? Okay, say that again. 6 point something. 7.5. Okay. Based on a glance, are these two numbers the same? No. All right. So that means this is wrong. G is not proportional to D. And that should make sense, friends, because proportional means that as D goes up, G goes up. Is that what happens? No. Come on, Kay. That's not right. All right, what do we do next? Okay, so what do you think it is? Inversely proportional. So that means that we're going to do something like G is proportional to 1 over D. So that would mean that G is equal to some constant K divided by D. You with me there? Okay? Or you could say that K is equal to G times D. Apple people, make your calculations. Moon people, make your calculations. Let's check it. Check with your other people that have the same object that you do. Make sure they've got the same number, so you've got a number and you can compare it. All right, Apple people, what you got? I want 6 point something. 10 to the what? 7? Moon people, what'd you get? They're closer? But again, if this is true, like if this is good physics, then these things should be really close, right? I mean, they're closer than these two were. I'm just saying. But they're not really very close, are they? I think the division is a good choice. But I don't think we're quite there. Suggestions? 1 over G is proportional to D. That's going to be the same thing. Because if you would flip them, you flip them both. Does that make sense? Yeah, so that, it's a good idea, but it's actually the same. It's going to be the same thing there. We're getting close, but the game is here, friends, that as G gets bigger, G's got to get smaller faster. What do you want to do? Square what? The D? Let's square it. G is proportional to 1 over D. Is that what you mean, Jacob? Is that what you want? Okay, so that means that if we're going to put a constant in there, we've got G is equal to K over D squared. So we could write that as K is equal to G times D squared. Let's do it one more time. Let's see if this one works. Apple people, do your thing. Moon people, do your thing. This is the same game that physicists do all the time. They've got data. They have to fit it to some sort of curve. You're doing what Excel does. You're doing what Google Sheets is doing right now. You're just doing it with 2 points. How well do these 2 points fit the suggested curve? They don't fit a line. They don't fit a hyperbola. Do they fit this 1 over x squared thing? All right, Apple people, do you have a number?
3.99 times 10 to the 14.
Moon people.
Oh my. Are you
That's pretty darn close.
No, it's not.
Now, I want to remind you that 9.8 isn't really 9.8, is it? It's 9.81 stuff. And 6.38 isn't really 6.38, it's 6.38 stuff. These are approximated, right? We've been approximating the whole time. These two numbers are pretty darn close. If I was going to round this to the nearest 1, it'd be 4 times 10 to the 14th. If I was going to round this, it would be 4 times 10 to the 14th. I'm going to go with this is a good fit. So we have just now solved the problem. How does acceleration vary with distance? And we have done essentially now all that Isaac Newton did.
But he did it too.
Right, but so what? Like, he was also just born earlier. Good for him. So what we've gotten out of this is that the force of gravity we know it acts between two masses. Okay? We didn't explicitly do this part, but we've been doing the analysis for this for a lot of months. If one of the masses goes up, what's going to happen to the force? It's going to go up. If the other mass goes up, what's going to happen to the force? It's going to go up. We kind of know that. That's kind of an intuitive thing. We also know, I'm going to say, so as either mass increases, the force is going to go up. And we know that as the distance increases, the force goes down, but it goes down by the square of the distance, right? We're going to put those things together and write down this statement. Fg, the force of gravity acting between any two objects with mass, is proportional to the two masses divided by the distance between their centers squared. That right there is what Isaac Newton did to invent, in big air quotes, gravity. Now, I don't know about you, but when I look at this thing, I feel a little let down. Why? Anybody else? It's not an equation. What does an equation require?
Equal sign.
An equal sign. When Isaac Newton came up with this is as far as he got. He said there's a proportionality constant, but I don't have any idea what it is. It took them 100 years to figure out what the proportionality constant was. 100 years to figure out what the proportionality constant was. There was this guy named Cavendish, and he's the one that figured it out. I'm going to show you how he did it real quick here. He gets none of the credit. Nobody's heard of him before.
Cavendish apples?
Is that a thing? I don't even know. Is it?
Isn't that a type of apple?
I don't know. It should be, but I don't know. All right. So this is what he did. This is really, really ingenious. Again, 100 years after Isaac Newton. Like, this is a long time. For a long time, they just sat with that proportionality. Okay, what are we going to do with this? I don't know. Anyway, Cavendish came up with this setup. It's brilliant. He has a string, and on that string, he puts a rod with two objects on it with mass. Right? We know the masses of them, and it's nicely balanced with all this torque stuff going on. It's beautiful, right? Okay? And then he brings another mass close to this one. If I've got a mass in close proximity to another mass, what's going to happen, friends? Two masses. What's going to happen? A force of gravity between them. And it's always an attractive force. Is it going to be a big force or a small force? Pretty little, given that these things are things that people can hold, right? But it was ever so slight enough that it caused this to turn, to rotate. And this little light source, I would imagine it as a laser. They didn't have lasers at the time, but we would imagine it as a laser now. Bounced off of this mirror, and it bounced, so angle in equals angle out. That's how a mirror works, okay? It moved the light that bounced ever so slightly that we could do the geometry to figure out how much this moved. I know the masses. I know the distance, okay? I know the acceleration. I can find the proportionality constant. You have to know everything else about the system in order to find that proportionality constant. It took him a whole long time to do this, but eventually the guy, his name was Cavendish, again, I just want to give him the credit that is due. I don't know any scandals about him, but I haven't honestly looked. So there might be stuff I just don't know. Okay? He is the one that put it all together, that made it clear to us how the universal law of gravitation works. Fg is now equal to, we use a capital G for this. Capital G for the universal gravitational constant. I'll tell you the value in just a minute. Times m1 times m2 divided by r squared. So just to be clear, we use radius because we're talking about things orbiting a lot of times, but r is just the distance. Between the center of mass, or I'll say distance from center of mass to center of mass. That might be better. And it's always written as R, which is why that's why I put it that way. M1 and M2 are just the masses. Fg obviously is the force. The universal gravitational constant has a value of, are you ready? Here it comes. 6.67 times 10 to the negative 11th. Okay. Took them 100 years to figure it out. There it is. I need to know the units of it, though. You have enough information to figure out the units of it. Go ahead and do that right now. Figure them out. You got this. Did you look it up?
So together with Cavendish and Newton,
They could make it like a smoothie?
apples and bananas.
I love it. I love it. There's that song that like the preschoolers sing, right? I like to eat apples and bananas. Oh, now it has a whole new meaning. Like my daughter was literally singing that this morning on the way to school. And now it's going to be, oh, thank you for making that better to me. All right. What are the units for this crazy weird number? What'd you figure out? Anybody? Oh, friends, come on. FG, what are the units of FG? What's a force? It's a Newton. Let's just leave it in newtons. I mean, you can do it that way too if you want. Masses are in kilograms. Radius is in meters. So to get all the units to cancel out, what's it got to be? Yep, that's how it's usually written. Newton meter squared per kilogram squared. You can cancel stuff out too if you want to, if it makes you happier to do it that way. This is the way I usually see it written though. It's just called no, it doesn't have any name. I need to find out if there's any like big scandal about him because I know nothing. Now, I want to make sure that this is all kind of sitting well with you because earlier in the year, we would just write FG as mg, remember? Like until today, if I asked you to find the force of gravity acting on an object, you just do the mass times g, right? M times 9.8. What I'm telling you now is that this is just a simplified version of this big fancy thing. So if I write this big fancy thing next to it, we can figure out what's going on. So that's g m1 m2 over r squared. So there are two masses acting here. There's only one mass over here. So this one here is like the mass of the frog. Let's say this one is the mass of the frog. Everything else goes into little g. Everything else goes into little g. So that means that little g, the acceleration due to gravity, we generally think of on Earth, is equal to g m2, which is the mass of the Earth, divided by the radius of the Earth squared. The mass of the Earth is 6 times 10 to the 24th kilograms. The radius of the Earth, I told you before, but is 6.38 times 10 to the 6th. I would like you to tell me what the value of g is. You can do that, right?
Wait, what's big G?
6.67 times 10 to the negative 11th.
What is it mean?
It's the universal gravitational constant. I guess I didn't write that out. Let me write that out for you while you're doing your calculation. How are we doing? Did you get it?
Not yet.
Working on it? What number are you expecting? Yeah. So hopefully you got that, or something close. Did you not? No? So 6.67 times 10 to the negative 11.
Did you square the radius?
Did you square the radius? Wah, wah. That would be it. 6 times 10 to the 24th. 6.38 times 10 to the 6th. But you got to square that on the bottom.
Actually, 6 million, 200 times 62.
Yeah.
700 times 2.
What'd you get, Grace?
I got, I got 9.8.
Yay!
Yeah.
Are you just being obstinate, or are you struggling?
I have a different answer.
What did you get?
I'm pretty.
Okay. I thought we were.
That makes me so
You should increase it since I count as a loss. How dare you discount it?
You wouldn't see it.
I would-
That was
I would feel bad. You guys doing okay?
That was funny though.
Yeah? All right. We have just enough time. This is perfect timing. I was reviewing this stuff and getting ready for this class, and then they made the announcement on earlier today. Was it like right before lunch or something? About prom, right?
I think so.
And friends, this is like the perfect time for this. It's like it worked out just right. The planets were aligning in some such way that I have an opportunity for you. I know that don't put your stuff away because we got one more question to do. Don't put it away because this is important.
Okay, yeah.
Okay.
Ask.
Okay? I know that at this time of year, people get a little nervous, like some people have that special someone and some people don't. Some people have like that special someone that they have in their brain and they're like, man, if only I could get up the courage to ask that person to prom, or maybe just out for pizza, or whatever it is. And today, you guys, I have it for you. This is it. The perfect way, not a joke, a genuine, heartfelt opportunity for you. Here's the thing. You have the opportunity to go up to that special someone, whoever it is, and say, hey, did you know that I'm attracted to you? But not only am I attracted to you, here's the important part, you guys. This is the key. This is the clincher. This is what's going to make it happen. Not only am I attracted to you, but you're attracted to me too. The same amount, right? Because you have two objects with masses, right? And that means that there's a gravitational attraction between them. And I'm telling you, friends, that is the knockdown best ask out line that I've ever heard. It is gonna, it's not a pickup line because that's kind of awkward. I don't, but you know what I'm saying? I think it's the thing, I think it's gonna work. Now, when you use this, unless you use it on another physics person, they're gonna know and they're just gonna say yes because they love it and they think it's nerdy and you're just gonna be like nerdy happy people. If they don't know this though, they're not gonna realize that the force is pretty small. I'd like you to figure out how small that force is, but the thing is that it's a mutual thing and that's the key. That's what's gonna make it happen. I'd like you to do the math here real quick. to figure out if you got a 50 kilogram person and a 75 kilogram person sitting next to each other on a bench, 3/4 of a meter apart. They're attracted to each other. They really are. I want to know the magnitude of the force that one person has on the other.
Okay, I got this.
You got this. This is it right here, you guys. It's perfect timing, just in time for prom. It's a beautiful thing.
Yeah. Times 6. What is it? 6.67 to the negative 11 times.
So you've got your two masses, you've got that universal gravitational constant. The universal gravitational constant is bringing you guys together. You see what I'm saying? It's a beautiful thing.
I got, wow.
Did you square your meters?
Yep.
Okay, you gotta make sure you do that, because otherwise the force will be too big. We don't want that.
It's too small.
It's not a big answer. It's certainly not. So FG, the force between those two people is what?
0.000000445.
10 to the negative 7th, is that right?
Yeah.
So it's not a big force, but it is there. Try it out. I'm telling you, it's gonna make a difference. Have a great day, you guys. We'll see you tomorrow.